Let's look at question 4C. This asks us to draw the logical circuit diagram of a BCD to 7-segment decoder and write its truth table. The model answer provides a clear definition up front. BCD to 7-segment decoder converts 4-bit BCD input to 7 outputs A to G for display. You see these displays every day. This vintage clock radio uses a 7-segment display. Each physical digit is constructed from 7 individual LED segments. To control those LEDs, we use a decoder. We feed 4 bits of binary-coded decimal data, A, B, C, D, into the left side. The decoder processes this, sending signals out through 7 lines on the right, labeled A through G. Computers process information in binary code, but humans read decimal numbers. This decoder acts as the bridge between those two formats, taking machine-level logic and translating it into a number we can instantly recognize. With 4 binary inputs, the system generates 16 possible combinations. However, the BCD system only translates to decimal digits 0 through 9. That means we only need the first 10 rows of our truth table. The remaining 6 rows are discarded. Before we fill this in, pause the video here. Test your memory and write down the 4-bit binary equivalents for the decimal numbers 0 through 9. The most difficult part of building this truth table is remembering which letter corresponds to which physical light on the display. Instead of guessing, use this simple pattern. Start at the very top. That is segment A. Now trace clockwise around the outside edge. B, C, D, E, and F. Finally, finish by crossing the middle belt for segment G. By keeping this physical mapping in your head, you eliminate the need to memorize a massive table of ones and zeros. You can mentally trace the shape of any number and logically derive which segments need power. Here is our blank truth table. The 4 BCD inputs sit on the left side of the ledger, and the 7 output segments sit on the right. Let's start with the decimal number 0. Its binary input state is 0, 0, 0, 0. To draw a 0 on the physical display, every outer segment needs to turn on, but the center line stays dark. So we place a 1 under columns A through F and a 0 under column G. Now look down at the row for the decimal number 8, where our input is 1, 0, 0, 0. The number 8 requires the entire figure 8 pattern. Every single segment must be active, so we write a 1 across all 7 output columns. By applying this physical trace method to the remaining digits, you generate a complete map. This table defines the exact hardware conditions required to handle every possible valid input. Once the truth table is filled, the raw data is grouped into Karnaugh maps, 1 for each of the 7 segments. These maps simplify the data into a set of Boolean logic equations using standard AND, OR, and NOT operations. Those equations translate directly into this, the final physical circuit diagram. While it looks dense, it operates as a series of layered decisions. If we follow this single path from the inputs through the logic gates, we can see exactly how the circuit decides whether or not to send power to segment A. Do not try to memorize the entire wiring layout. Master the block diagram and the physical layout mnemonic. Once you can accurately construct the truth table on your own, you possess the logic required to build the entire system. Take some time to practice mapping the truth table by hand. Good luck with your studies, and thanks for watching.